This morning I want to focus on supplementary topic 1, and this is on states of matter, whether things are solids, liquids, gases, and we're going to look at transformations between those different states of matters. So we're going to look at them, what defines them, look at heat and temperature as a function of what's going on here, effective pressure on boiling point, molar volume at the end, that sort of thing. A lot of the early experimentation was done on gases, and we'll look at that in a little bit more detail today and also, or this morning and this afternoon. But I'd also like to remind you that at the very beginning of this course I mentioned that the ancient Greeks, Empedocles, considered that all matter was made up of just 4 things: earth, water, wind and fire. And I suggested to you that that was a really good choice, because what you have in those 4 things is a solid, a liquid, a gas, an energy change. And that's really the focus of the 2 lectures today. And what I want to start off with is just looking at the states of matter, whether they're a solid, a liquid, a gas, and what the difference is between them, and what happens when we transfer one to the other. Well, I think you're all familiar with those states. But just to think about them in a little bit more detail as to exactly what's happening on a molecular level when I've got a solid, a liquid, or a gas. And if we think of what's happening to the particles, it really comes down a little bit to motion of particles. In a solid, we have our particles fixed relative to one another, whether it's an ionic solid like this and the cations, the anions are all lined up in an extended 3-dimensional array, or whether it's a molecular solid, let's say an ice cube, which we could decide has a model, has a structure indicated by this model. We've got an irregular array of materials. Now, the problem with models like this, it suggests the whole thing is static, whereas in actual fact, each molecule can vibrate and move a little bit within the solid. As you cool down the solid, then you can cool down that ability to move, and I can perhaps demonstrate that if I take some liquid nitrogen, which is in here, and we'll have a look at that liquid nitrogen in a moment. But I can take some materials that are relatively flexible, I can cool them down. An ant seems to have got onto my safety glasses. I can cool them down into liquid nitrogen, and while the solid looks like it retains its form, I've actually reduced the flexibility of the material enormously. And to show that again with one of my sort of favourite flowers, a kangaroo port. And freezing materials, while it's not actually so useful for flowers because they become brittle, you change the structure of the material, it can be useful for some foodstuffs. If you freeze them very fast, then the water present in the foodstuff doesn't have a chance to crystallise out into large ice crystals. So you get a whole lot of very small ice crystals. When you defrost the food, those ice crystals melt and you retain a lot of the original structure. If you freeze something slowly, then as the liquid water in the material forms ice, the ice crystals grow and they pierce the cell walls. That then means that you've lost the structure of the material when you defrost it, and when you defrost it, it goes to a mush. So snap freezing is used, for example, in things like freezing strawberries or materials which contain quite a lot of moisture. So cooling things down, cooling even a solid down, you can reduce those molecular motions. And perhaps as one more example there, we're familiar with the flexibility of rubber tubes, for example, and if I say remove some of that flexibility by cooling that tube down, its physical properties change and it becomes hard and brittle. And in fact, this sort of technology had to be worked out when the guys first walked on the moon, because, as you know, Americans, they have sneakers, and normally sneakers are made out of rubber, but the surface of the moon is sufficiently cold that the rubber freezes solid, so there's no flexibility in it on the surface of the moon. So what they did was actually change the rubber, which is made out of a compound of carbon, to a rubbery material made out of compound of silicon instead. So silicon's below carbon in the periodic table. There are many properties that are similar in terms of the chemistry and the bonding. You can get things called silicon rubbers, which retain some of this flexibility, this elasticity, but they transit to a brittle, hard structure at a much lower temperature, and so that they were suitable for making moon boots out of, because the moon boots would then retain some of that flexibility even at the low temperatures. Well, in here there's liquid nitrogen that's about minus 160 degrees C, and if I was to just pour it out, you can see that it's a very non-viscous liquid. It evaporates pretty much instantly at room temperature. Keep it in a thermos flask to keep it cool. So one thing we're going to look at is the transformation between states, liquid to gas, solid to liquid, and so on. But let's just focus a little bit more on what it means on a molecular level when we have a solid, a liquid, or a gas. We're familiar that a solid, one of its characteristics is it retains its shape. A liquid adopts the shape of a container that it's in, and so it can change its shape, and the difference really between a liquid and a solid is that the particles in a liquid have much more translational motion. They can move around with much greater ease. You find the densities of solids and liquids tend to be fairly similar, and pretty much in all cases except one, the density of a solid is greater than the density of a liquid. That means that the particles in a solid are packed a little bit more carefully, a little bit closer. In a typical liquid, there's only about 3% spare space. So there's a little bit of wiggle room, but not a huge amount. A gas, on the other hand, is quite different. The particles in a gas occupy the entire volume that's available to them. It's characterized by a large amount of space surrounding the gas, and as a consequence, in something like water, 1 ml of water will give over 1.5 litres of gas if I heat it up above the boiling point. So a very large space. What this means is that the molecules or atoms are widely dispersed and don't interact with each other to any great extent in a gas. They're just too far apart to interact. In a liquid or a solid, however, you can get that interaction. And I mentioned yesterday that water in particular has a very characteristic interaction that we call hydrogen bonding. And in this model of ice, we have at each joint an oxygen attached to 2 hydrogens nearby, and then there's a longer bond. We call this a hydrogen bond. It's an interaction between separate water molecules. And we have, even in ice, where the bonding, the formal bonding, is within the H2O molecule, we have a much longer range order available. Water is exceptional in many, many ways. We've seen its use as a solvent, but one of the exceptional properties is that the ice structure happens to have a density that's slightly less than liquid water. And you're familiar with, for example, ice floating on water. And if it didn't float on water, then life as we know it, probably wouldn't exist. What's actually happening when I have a solid, a liquid, is that all molecules, all particles, have some interaction between them. It's not nearly as strong as covalent bonding, but it's like a solvation that we talked about with ions dissolving in water. In the case of solid water, this hydrogen bonding gives a fairly open network. If I now think about what happens when ice melts, I'm increasing the temperature from below zero to above zero, putting in a little bit of energy. And that energy gives the molecules a bit more energy in which to move, and a point comes when the molecules have enough energy that they start to be able to overcome this rigid structure. The structure collapses and we get water at, let's say, just above 0 degrees C, which has in fact a more compacted arrangement of water molecules which are just moving around. They are hydrogen bonding to neighbours, but then they have enough energy to break that hydrogen bond and bond to further neighbours. As you heat up that water, you're providing the water molecules with more and more energy. They move around faster and faster, and the point comes when eventually a water molecule can overcome all the attractive interactions that it has with neighbouring water molecules, and so be released into the gas phase. And that's where boiling then occurs. So think about for a moment what might happen when I boil a liquid. We all know what it looks like. We all know that there's, bubbles in a liquid. But the question is, what's actually in those bubbles? And I suspect actually if you ask quite a few of our students, they would come up with a wide variety of answers, hopefully one of which would be right. What's happening in those bubbles is that you've got water vapour, but because gas is very much less dense than the liquid, the bubble contains very little water vapour compared to the H2O in the liquid. It's much less dense, so it rises through the liquid. It contains a lot of, if you like, spare space, but it is H2O gas molecules that are present. And in all cases, when I go from solid to liquid to gas of any substance, I am looking at retaining any covalent bonding that's present. So water is an H2O molecule, whether it's in the solid, the liquid, or the gas phase. And it doesn't break up into hydrogen and oxygen. Think of the problems there would be if it did. We've had a look at a couple of reactions with H2 exploding with oxygen or burning with oxygen. And if just every time you boil the kettle, you produced hydrogen and oxygen, the component parts, then we'd live in a very sort of flammable environment. And that's not the case. Now, another thing with the water is if I think about these interactions between the molecules. So for a water molecule in the middle of the bulk of the liquid, it has some interactions with water molecules all around it in 3 dimensions. And the pull, if you like, between the neighbouring water molecules and the H2O in the middle there is the same in all 3 dimensions. If, however, I have a water molecule at the surface of the liquid, then I get forces of attraction between that water molecule and neighbouring ones at the surface and down into the bulk of the liquid, but there is no upward force to balance that. No water molecules on the upward side. As a consequence of that, we get this thing, surface tension, where there appears to be a little bit of a skin on the liquid because there's a net downward force pulling the molecules down that is not compensated for by a force in the opposite direction. We can see a consequence of this if we have a small, very small water droplet that is sufficiently small that it's not subject to gravity, then we see it forms a perfect sphere, which is a way in which the molecules have of sort of minimizing this imbalance of interaction. And we can get an idea about how strong these forces of attraction between molecules are by the degree of surface tension that the liquid shows. Water has quite a high surface tension because it's got quite strong interactions between the water molecules. But what I want to look at is actually what's happening when we go from a solid to a liquid to a gas and vice versa. Now, you're familiar with the fact that if you take a solid, let's say an ice cube, you've got to put heat in to melt it. And in the case of the ice here, then it's going to be heat from the room. You've got to put heat into a liquid to create a gas. So going from left to right, you put heat in. And that is the case in all situations. The converse is also true. If I condense a gas to a liquid, heat is given out. If a liquid is frozen into a solid, heat is given out. Think about what happens when you put, say, a tray of ice cubes or a tray of water to make ice cubes into the freezer. You're doing the cooling process, the freezer turns on because it has to do a bit of work to take away the heat that is generated when the water freezes. And if I look at a graph of the temperature of a material versus, let's say, heat put in, then it will look something like this. If I start off with a solid and put heat in, the temperature rises. And each solid has a characteristic slope to this part of the graph. But then a point comes when the solid starts to melt, and at that point the temperature doesn't change, and all the heat that you're putting in goes to melting the, let's say, the ice to form water, and the temperature stays the same, 0 degrees C in the case of water. If I then have melted all the ice and continue to put heat in, I raise the temperature of the water from the freezing point, melting point, up to a point where the water begins to boil. And at that point, when I've got liquid and steam present, putting in extra heat will not increase the temperature, it will just go to boiling the water molecules into the gas phase. And only when they've all gone will the heat start to increase again. And I want to try and show you that. These flat areas are associated with what we call latent heat. And in the case of water, going from the liquid to the gas, there is an awful lot of latent heat associated with that. As a consequence of that, if, for example, you go from a gas to a liquid, steam to liquid water, a lot of heat's given out, and the consequence of that is that you can severely burn yourself with steam. In fact, you can get very severe burns with steam, because as that condenses to water, say on your skin, then a lot of energy is given out, and your skin absorbs that energy to its detriment. Now, I'll just turn that off. Yeah, look, my simple demonstration is that I've got a temperature probe in the kettle, turn on the kettle, and what I want us to do is just have a look to see what happens to the temperature as the water heats up. And I think we will see, I mean, you will know what boiling water looks like, so you can imagine what's happening in the kettle, but I'm putting in a constant amount of heat electrically through the element in the kettle. The temperature is rising steadily as the water gets hotter. And we're starting to get small bubbles occurring from some localized heating. As the kettle approaches boiling, I'm still putting in the same amount of heat all the time. And now we're at, the water's boiling. Temperature probe is just catching up here. And what I'll do is move the kettle on the downwards. So, what I hope you can see is that, notwithstanding just a little bit of calibration needed for that temperature probe, I'm still putting in the same amount of heat, and yet the temperature is constant. And that's because all that heat is going into boiling the water, removing every water molecule from its neighbour in the liquid, and that temperature will remain constant until all the water has gone. At which point the kettle will get very hot and there'll be a bang as a plug shoots out the back. So our temperature profile then of any material looks something like that. And these flat areas we associate with what we call latent heat of fusion, latent heat of boiling. And each of these transformations between solids, or liquids and gases, have a specific name. And you're familiar with many of them. And if I just run through those, let's look at transformation between a solid, liquid, and gas. So, solid to liquid, melting. Liquid to solid, freezing. Liquid to gas, evaporation. And gas to liquid, condensation. And there is another couple where if I go from solid to gas directly, we call that sublimation. And gas to solid directly, we call that deposition. And looking at a couple of practical things, if you want to cool something down, it's not very efficient just to put it in ice, because we know the structure of ice, a solid retains its structure, and the surface area of contact between solid ice and your object you're trying to cool is relatively small. Instead, cooling is much more efficient if you put it in an ice bath where you have a mixture of ice and liquid present. And in that case, because the liquid fills the base of the container, it will surround your object, whatever it might be, and cool it nicely. And there'll be good heat transfer between the ice and the liquid. So always, if you're cooling anything, use a slush of ice and water. Now, for sublimation, particles that don't have a lot of attraction between the molecules, or situations where you don't have a lot of attraction between the molecules, may turn straight from the solid to the gas. And an example of that is dry ice again, and we saw some of that yesterday. And let's just do the same sort of thing and think about this a little bit more carefully. What you're seeing is gas being given off. Dry ice, solid carbon dioxide. If I warm it up to somewhere above room temperature by putting it in water, we're seeing gas given off. You don't see the CO2 going to form a liquid. It goes directly to a gas, which is bubbled out of solution. So CO2 is unusual in that it sublimes at under room conditions. We can also see here that I've got white stuff. This white stuff is not carbon dioxide as such. We've got carbon dioxide there, of course, but what's happening is we're getting a condensation of the water vapor that's in the air down into liquid water that we're seeing as sort of white, well, steam is the wrong word, so condensed water, because of the cooling effect of that carbon dioxide being given off. Okay, so what can we say about something of the sort of theory behind all of this? Well, it's encapsulated in what we call the kinetic molecular theory of materials, and that's really associated with movement of molecules. And we're saying that if we take, say, a gas, then the phenomena of gas pressure is associated with gas molecules moving and hitting the side of a container. At a particular temperature, the kinetic energy of all gases is the same. And I want to try and just show you one of the consequences of that. So, quick recap. At a particular temperature, the kinetic energy of all gases is the same. Kinetic energy is associated with a speed and also a mass. So if we look at, say, a gas at room temperature, all the molecules are whizzing around at a particular speed. All the molecules in the atmosphere have a particular kinetic energy, but because they might have a different mass, the actual speed with which they're going may change a little bit. And if I increase the mass, I will decrease the velocity and vice versa. Now, what I've got over here is a porous pot. So this allows gas through it. There's gas on the inside, gas on the outside. There's no pressure difference either side of that porous pot. Now what I'm going to do is actually put some hydrogen around the outside of the pot. And then what you might be able to see that there's now a flow of liquid actually over there on the bench. So what's happening there? And that will remain for a while. If I take that off, blow away the hydrogen, the flow of liquid will stop, and moreover, I'll start to see bubbles in the bottom there. So what's happening? Hydrogen is a very light gas. As it's a very light gas, its velocity is very high. Now, when I have an ordinary atmosphere on both sides of that porous pot, then because all molecules are in constant motion, then there are gas molecules coming out of the porous pot at exactly the same speed as gas molecules going into the porous pot, and we've got a balance. If now I put a light gas like hydrogen around the porous pot, then because the hydrogen molecules, they're light, they're travelling fast, there's more going in the porous pot than there are gas molecules coming out, which on average tend to be slower. And as a consequence, the pressure builds up inside and I squirt the liquid out of the nozzle. Conversely, after a few moments, I've now got hydrogen on the inside of the porous pot, remove the hydrogen from the outside, so it's ordinary nitrogen and oxygen. The hydrogen molecules are moving faster. They will move faster going out of the pot than ordinary atmosphere. Nitrogen, oxygen molecules move into the pot. And as a consequence of that, then a pressure difference arises, and then that pressure difference means that the extra atmospheric pressure pushes air into the apparatus at the bottom there. So just to try that one more time. The apparatus is at equilibrium. That means the air molecules moving through the pot in both directions occurs at the same speed. I can do this easily with hydrogen because it gets trapped in the beaker there, and if I fill that beaker with hydrogen, I can see that I have changed the pressure, got a bit of a pressure differential, more hydrogen molecules going into the porous pot than coming out of it. Reverse that procedure. I've now got more hydrogen molecules on the inside relative to the outside. They're travelling faster, so they will move out quicker than the air will move in. I get a pressure differential, and air gets sucked in through the apparatus. So it's sort of experiments like that that are used as evidence to suggest that there's a constant motion around the particles present. And the last couple of things I want to say, and really related to that and related to air pressure. When a material boils, when a liquid boils, then we need to release the molecules of that liquid into the atmosphere. How easy that is to occur depends on the force of attraction between the molecules in the liquid, and it also depends on the weight of the atmosphere. And on Earth, we've got, or at sea level, there's about 1 kilogram of air per square centimetre as a downward pressure. And that acts against releasing the molecules from a liquid. If I look at a situation of reduced pressure, such as top of Mount Kosciuszko or even Mount Everest, say, where there's less pressure of air at that level, then it's easier for the water molecules to escape from the water into the gas phase, And as a consequence of that, then the water boils at a much lower temperature. So topical Kosciuszko, water boils at 90 odd, about 94, something like that, and it's quite a bit lower at the top of Mount Everest. Now, one final thing to say is really relating to different types of gases. The characteristic of a gas is that the molecules don't interact with one another. There's a lot of empty space. So imagine a situation where we take 1 mole of gas. We find that the volume of 1 mole of gas depends not on the type of gas you have, but it depends on pressure and temperature. And I'll say more about that this afternoon. So if I reduce the pressure, the volume expands. If I increase the temperature, the volume expands. The interaction between gas particles is very small. As a consequence of that, 1 mole of any gas occupies the same volume, but the density of it is different, and we can actually measure the molar mass of gases based on molar mass of materials based on the density of their gas. So it turns out that the molar mass of it turns out that 1 mole of any gas occupies about 24.5 litres at room temperature and pressure. Because different gases have a different mass, then that 24.5 litres will have a different mass depending whether I've got hydrogen or carbon dioxide, and as a consequence the density of the gas is different. Hence why something like a hydrogen balloon or a helium balloon floats, because the density is so much less for a given volume compared to the surrounding atmosphere. Okay, look, I will leave it at that, and we'll finish off gases this afternoon and look at enthalpies.